if you could go anywhere and you had an unlimited budget, what space mission would you like to see done, and what would it address?
Oh, you've really got me now. You've got me.
You're listening to The Cosmic Cast. Brilliant. Well, welcome. I'm John Fanny Fisher. I'm joined by Thomas Harvey.
Hello,
and Dr. Richard Parker from the University of Sheffield. Hello.
Hello.
So thanks very much for joining us today. So you're into stellar formation, and so I guess what we were thinking about earlier was, how did you get into this field, and what are the sort of big questions, the big picture questions that really sort of drive you in the morning to sort of get up and go to work and tackle some of these issues?
Well, I think I've always been interested in planets and planet formation, and when I was an undergraduate at the University of Sheffield, really didn't have anyone who worked on star and planet formation per se. So the final year of my undergraduate, a new lecturer turned up, and my PhD supervisor, Simon Goodwin, and he was the first person that they'd had who really looked at the kind of the theory or the fundamentals of star formation. And I wanted to stay in Sheffield. That was sort of one of my motivations, but I also wanted to work on something that I thought was dynamic and interesting. And I was sort of advised that the best way of doing this was to work with a relatively young academic, and Simon was at the time quite young. And so I was sort of almost kind of fell into doing PhD on star formation. But one of the things I was always interested right the way through was, can this be applied to planet formation? What do we know about star formation that could inform our ideas and our theories about how planets form and evolve? And so that was always at the back of my mind. Actually, during my PhD, I did very little planet formation. But since then, I've been more sort of interested in the planet formation side of things. In order to understand the planet formation side of things, we really need to know what the environment of star formation is. We know that planets form at the same time as stars. So planet formation is star formation. And so we need to know, what the typical density of star forming region is. What are the environmental conditions? What's the extra physics that's going on aside from just gravity and converting gas into stars? And so that's the sort of main reason I think I'm interested in star formation. That's the outstanding problems are we don't really know what the typical initial conditions of an average star forming region is. And then if we talk about planetary systems and host stars, our sun, for example, we don't really know the type of star forming environment our sun was born in and what the sun underwent as a very young star when it was still forming its planetary system.
So we don't really know if this solar system is a bit of an oddball or is representative of other solar systems.
That's right. So it could be completely atypical. We know that from observations of other stars that have planets, we know that maybe half of them have sort of a Jupiter mass planet at around about the same location that Jupiter is in our solar system. But then on the other hand, we know from observations of Kepler that there's lots of rocky planets that are very densely packed and very, very close to their host stars. And we don't have those type of planets in our solar system. So that begs the immediate question, well, what was the difference in the route that those planetary systems went compared to our own?
Yeah, I mean, it's very interesting for sure. So are they sort of nailing down on some of these exoplanets then? Do you see that as the future really of trying to understand other solar systems and the context in which?
I would say that we have a pretty good idea observationally of what the, I always like to call it the architecture of planetary systems. So, we know, I think we have a good consensus of, how many planetary systems have lots of rocky planets that are very close into their host star. These are often called the so-called Kepler type systems because they were discovered with Kepler. And we also know kind of roughly how many planetary systems we might expect have, gas giants at the same location as us. And I think that you'll never ever find an exact analog of our planetary system. There will always be some sort of difference. And we know that the early evolution of our solar system is probably very stochastic. And in fact, the subsequent evolution of our solar system may end up being very stochastic as well. And so I don't think you'll ever find an exact analog, but trying to kind of pin down how many solar systems are like ours, how many have these gas giants at kind of the same location that Jupiter is. That gives us a footprint, but I think that's only the start, because what we want to understand is, are there certain things about our solar system that are conducive to life developing? And I don't think just saying, okay, this planetary system kind of looks like ours is answering that question particularly.
Yeah, and I guess that's the big question really, is life ultimately. I mean, what do you think? Do you think there is other life out there? Do you think we will find a solar system that's a good candidate for hosting life?
I like to think so. I like to think so.
You're an optimist.
I'm an
That's
optimist.
Good.
I'm an
That's
optimist.
Good.
I think there has to be a new way of thinking about this, though. I'm not just saying this because I'm currently in a department that studies geochemistry and cosmochemistry, but we know that there are certain things about our solar system from a geochemical point of view that are perhaps slightly unusual. So, for instance, we think that the oldest objects in our solar system have these so-called short-lived radioactive isotopes, so chemical elements that are not expected to be long-lived. They're versions of more stable chemical elements, such as aluminium-27. But we know that there are the short-lived radioactive isotopes, aluminium-26 being the main one, that there appears to be more of it in our solar system than you would expect, just from measurements taken within the galaxy. And so the question's got to be, we know that potentially the long-term effects of these radioactive isotopes is to contribute to the heating that goes on inside our planet. And we know that this heating potentially can sustain plate tectonics on Earth. And plate tectonics are often thought of as being a very destructive thing. So you have volcanoes, you have earthquakes, and you have tsunami, and they create havoc to millions of people on our planet. But then without plate tectonics, you can't keep the carbon cycle going on the planet. You can't sustain potentially an oxygen-rich atmosphere without plate tectonics. And so if this aluminium-26 is contributing to plate tectonics, then it might be that the whole reason that we have a sustainable, breathable atmosphere on our planet might be in some part due to these radioactive isotopes. Mm-hmm. And so we need to understand where they came from, how many planetary systems have this inherently within them, if we want to understand potentially why intelligent life broke out on our planet versus any other planetary system.
And do you think we'll find such intelligent life in our lifetime? Or is that too much of a technological leap?
I think we need to start off by saying, okay, well, we've identified certain things about our planetary system or our stellar system that may have helped life to develop. Can we look around nearby stars and see the same thing? Mm-hmm. So one thing that might be possible in the future is we can study the long-term evolution of planets that have this internal heating from these radioactive elements. We might be able to say, okay, we expect planets that have this internal heating to look very different to planets that don't. And by very different, I mean they might have a slightly different radius or size. And so if we can somehow search for planets and try and categorize planets around other stars that might have this radioactive heating versus those that don't, we can then maybe focus our efforts to look for signs of intelligent life around those stellar systems and those planetary systems.
Yeah, interesting.
Okay, I got a question. Speaking as someone with a very geology-heavy background for coming to planetary science, I'm very used to dealing with samples, rocks, whatever it is that we're looking at. I suppose the question would be, what sort of data do you tend to work with? What's it like handling presumably massive data sets of that sort?
Yeah, I mean, we tend to actually take when you talk about from a geological point of view, measuring abundances of chemical elements in rock samples, which is essentially what you're doing when you're looking at meteorites. We tend to take those measurements as read in astronomy, and the reason for that is that you can measure things to parts per million, right? You have incredibly exact measurements because you're doing this thing in a lab. Mm-hmm. In astronomy, we're lucky if we can measure things to a factor of 2. And so the sort of geological side of what I work on is very much more high precision science than the sort of astrophysical side of things. And so what we're doing is adopting a statistical approach. So what we want to do is run as many different simulations as we can, go through as much parameter space as we can to really try and identify, is there a particular set of parameters is there even an area of that parameter space that seems more feasible in terms of the long-term, what's more feasible initial conditions for the long-term evolution of our planetary system? And so I think if we can hone down on that sort of area, then we can then start to have a grounding of how much data do we really need, and how do we process that data. And I actually think that in our field, certainly the astrophysical side of things, I think we're actually quite a long way behind the curve, because we analyze the results on the output of hundreds or thousands of simulations, and we essentially do that by hand. We essentially go through every single simulation and try and understand if there's something abnormal or normal about that simulation with respect to our entire data set. And we're not yet at the stage where we can really throw machine learning techniques in order to handle these big data sets and to analyze these big data sets.
Presumably that's round the corner, though. I guess as computing power is getting better and better, there must be such a shift between what was done 10 years ago and today, say.
Yeah, and I think you see even... so I was finishing my PhD 10 years ago, and the way that data was analyzed then is completely different to how it's analyzed now. For example, advances in, I would describe user-friendly programming languages, in particular Python.
Yeah.
You see PhD students now just analyzing data sets in such a more efficient and kind of focused way than I did when I was doing my PhD. And I'm a dinosaur. I still use Fortran. Not that there's anything wrong with Fortran, but it's completely different. If you want to sort an array in Fortran, you have to do it you've got to write the code to do it. In Python, you just call a function and it does it for you.
Yeah, Fortran's not very nice. There are a few geochemical model programs that were written in I think the sort of late 70s, early 80s in Fortran that haven't been updated, and they're a bugger to use.
So I think the way that the young researchers in the field, and let's be honest, the people at the apex of the field are always the young people, right? They always have more energy, they have more time, they have more ideas, and I think what's happening at the sort of the end of the field where you have more junior people working on is really exciting, and I think that bodes well for the future. I think we're really going to start tackling big data sets in a really much more efficient way in the next few years.
And I guess that will probably help reduce uncertainties on some of these models and stuff. Just by sheer volume of numbers, I guess you can crunch more data and play around more.
And I think we're going to get better at sort of assembling our simulations and our models and even observations as well. I think we're going to get better at assembling those into databases where you're just going to be able to query a set of models. And I think people are already developing the kind of the software and the framework with which to do that, and I think that's a kind of a promising future avenue. I
think that's very important for sure. I mean, like just some of that metadata that comes with a lot of geochemical data, for instance. There's a few databases that collate geochemical data, but there's not much out there, and there's a huge amount of value through people pooling all this data together with all the relevant metadata, and as you said, doing these search queries to pull out bigger pictures, trends, and things like that. So yeah, it's very exciting, actually. I think for sure. Yeah. So you must have some pretty good computing facilities in Sheffield then.
We don't do too badly, but interestingly, I think advances in computing power in the last few years basically mean you can do a lot of stuff on a desktop.
Oh, really?
So,
okay.
A lot of the sort of, I'd say, kind of high-level analysis where we're picking into simulations and creating sort of graphs or ways of representing the data, that can all be done on a desktop. The simulations that we run where the main simulations I do two types of simulations. So one is what we call an n-body simulation, where you're literally just working out the force due to gravity on each particle and then doing that simultaneously for every particle and then moving forward in time. That has to be done on essentially computing clusters. But 10 years ago, you'd have to do that on a computing cluster that the university had invested a lot of money and time and resources into. And you'd have to share that with a lot of other researchers from different departments who have different needs in terms of the hardware and the software they use. Whereas now, we can essentially do that on a kind of inbuilt house system where we're just pushing together a few sets of processors. And in Sheffield, we have an astronomy group that has maybe 20, 25 people, including the PhD students and postdocs. And we all share this facility, and it's fine. It's essentially an in-house facility. If we want to do something more, how shall we say, more computationally intensive, then we can use the university's dedicated supercomputer. But we haven't had to use that at the moment.
That's cool. And much cheaper too, I imagine.
Yeah. And then the other type of simulation that I do is essentially a Monte Carlo simulation.
Yeah.
Essentially rolling the dice. So you expect a certain behavior of a system, and you can represent that system in terms of a few simple equations, and then you essentially sample the different equations to see, what type of outcomes would you expect. Mm-hmm. And that again is essentially, you can do that on a desktop.
Yeah. Cool.
What's it like interacting with the simulations? Is it a lot of setup and then you just wait until it's run and then see what it spits out, or is there maintenance that's involved? I know earlier you talked about one that took 2 years. So does that sort of thing just to start and let it run, or do you have to kind of really be involved?
So the simulation I showed that took 2 years was done by a different group. Mm-hmm. So I was showing a simulation where we're converting basically gas into stars. In order to do that, where you're going to form several hundreds of stars, that does take a couple of years on a supercomputer. And I think you have to kind of keep a check on that simulation mm-hmm. to make sure that it's not doing something unexpected or unphysical. But the sort of the simulations that I tend to do, or the gravitational n-body simulations, the effort going in to set them up is essentially kind of already been done. So we spent a few years refining the physical conditions that we put into those simulations. And then the simulations, we're essentially just doing one equation. So the force equals gmm over r squared. Mm-hmm. And so the simulations, you need to check the output, because those simulations can go wrong as well. But if you're happy with the output, for example, one of the things we do is we check that we're conserving energy in the simulation. As long as we're conserving energy to a reasonable accuracy, then we just let that simulation go, and then we analyze it at the end using a different set of software.
Cool. Well, we've got about 5 minutes left to go. So we've just got a couple of questions. They're a bit off the wall, perhaps. So, is there something that's not in your research area in the science field that you find particularly exciting?
Yes. I've been thinking about this a lot over the last few weeks, mainly because I was trying to pull together an interdisciplinary grant application. But it does interest me genuinely as well. Is we talk about, whether or not, we're the only civilization in the universe, mm-hmm. and how likely it is we're going to find alien life and all that kind of thing. And I wonder how much of the kind of the deliberation that we have about this is basically a philosophical thing, in the sense that, how much do we like the fact that we might be a complete fluke, a complete anomaly in space and time. And I think in order to address those kind of questions, I think we need to kind of involve some people who really understand thought processes,
mm-hmm. Some deep thinkers.
Logic and deep thinking.
Yeah.
So I would like to see us work more with philosophers in
Interesting.
Future.
That's interesting. Well, I guess, physics at the root is philosophy, isn't it? I suppose.
Yeah.
Yeah. I mean, it's got to be said, I suppose it's, it says a lot about society in general that, we've thought about alien civilizations since, hundreds of years now, since we've been able to systematically look at the sky. So that must say something quite fundamental about us as a society, I suppose.
And I think certainly as an astronomer, I feel quite lucky, because, I kind of joked earlier on that, we only understand things to within a factor of 2. We're certainly not an exact physical science. Yet if you talk to the layperson on the street, mm-hmm. they were always excited, almost always without fail, always excited to hear about what astronomers are working on, what the latest developments are. And I think we're very lucky to be in that kind of position where, we are essentially, very fortunate to be in this position where we can invest time and money into looking into this. And I think it's a really it's an exciting role to have.
Yeah, I think, a lot of people might say that it's a waste of time and a waste of money, but yeah, I think there's definitely a strong case to be had there, that some very deep questions to be answered about who we are.
And the thing about blue skies research, which is what astronomy is, yes, there may not be any immediate outcome, but some of the most amazing discoveries come from blue skies research. Lasers came from blue skies research. How many people go to a hospital and don't have something, to help their condition that is powered or by lasers. It's a fundamental thing in medical practice nowadays.
Yeah, well, and space exploration in general has fostered so many things that we take for granted today, I suppose. Interesting. So, finally, one last question. If you could go anywhere and you had an unlimited budget, what space mission would you like to see done, and what would it address?
Oh, you've really got me now. You've got me. I really don't know. I would like us to identify stars that are very similar to ours. So same mass, same chemical composition. And basically send a probe to each of those stars and see how similar or different their solar systems are. And maybe that's, obviously that's not technologically feasible now, but maybe in the future it will be.
I'd like to think so. I mean, that would be tremendously cool. I mean, it is seeing, some of this Kuiper Belt objects through new horizons is just fascinating enough. Just what another solar system must look like, and the sort of geological processes that go on there. Just really makes you wonder. And
I think if I had a sort of more refined goal, I would say I would like to go and see what it's like to be a planetary system either in or around a binary star system, because we know that binary stars make up a considerable stellar population in the galaxy. It might even be that we're unusual in that our star is not part of a binary or a twin star system, and so I would love to know what it's like being on a planet or orbiting one or both of those stars.
How far away is the nearest binary system? Is there one quite nearby?
The nearest star is a binary
system.
Is it?
Okay.
Yeah,
interesting. So that's Alpha Centauri?
That's right, yeah.
Okay.
Yeah. So, they're ubiquitous.
Interesting. And they're quite stable. They don't...
Yeah. So we think that basically when stars form, most of them are in either binary or we call them higher order systems. So these could be triples or quadruples. And the quadruples and the triples can be dynamically unstable, and they will kind of decay into a stable configuration. And often that's a binary star system and then two single stars. Okay. So that's why we have lots of single stars, we think.
So through Kepler, we observed what goes on in some of these binary systems. Do we have a rough idea of the sort of solar system architecture?
So we've observed planets around one of the component stars in the binary system. And then we've also observed planets with Kepler orbiting the entire binary system. So I don't think we're far off getting ideas of the architectures of these planetary systems. But it's interesting that they're actually, unless the two stars are really close together, it depends where you want to put the planet. But most of the time, planets are stable in binary systems. There are significant areas of the orbital sort of space where you can have stable planets. They're not affected detrimentally by the companion stars.
Interesting.
And we don't have any reason to suspect that planets find it harder to form in and around binary star systems than around single stars.
Yeah. I mean, that's that sort of thing out of science fiction, isn't it? Looking up and seeing two suns in the sky like that. It's quite cool. Cool, brilliant. Well, it's been a fascinating conversation. Thank you very much for joining us.
My pleasure, thank you.
No worries. And we'll be back next time with some more podcast action.
The only other thing that we'd ask is whether there's anything you've got coming up soon that you might like to shout out. Any papers that you'd like people to read?
Funny you should say that. So I was really fortunate. My first year as a lecturer back in Sheffield, I had really, really talented project students. And one of the students worked on basically calculating the habitable zones around the component stars of a binary system. And we basically showed that interactions in a young star cluster can push the two stars in the binary system closer together. And that essentially enhances or enlarges the habitable zone around the stars. So we often think about star forming environments or star clusters being very hostile places for planet formation. But actually, if you have a very close binary system that could have planets, you can increase the habitability of those planets through encounters with other stars. And so we've got a paper that's currently we're putting together a press release, and we've commissioned a a space artist should give us an
that's
artist
cool.
representation
That's
of,
very nice.
of the system. And basically, next few days, he's going to send me what he's come up with. So
Amazing.
Excellent. Well, we'll put a link to the paper
Hopefully by
on the
time
YouTube
this
channel
goes
in the
out,
description.
yeah.
So the paper is not currently out. So
Okay.
we're waiting for the press release to be put together, but I shall let you know when it is.
Brilliant. Yep.
Fantastic.
Really excited about that. And it was basically put together by my fourth year student, Bethany Wooten, who's did a brilliant job. So without her, would not have been possible.
Cool. Brilliant.
That's something for everyone to keep an eye out for then.
Excellent. Well, thank you once again.
Thank you very much.